methods that we have developed for the fixed mesh agility method for embedded meshes, and in particular for free surface flows. Okay, so this is the outline of the presentation. So the idea is that we want to be able to solve free surface flow problems by using a fixed mesh approach. And we want also to be able to focus the computational power that we need in the regions where it is needed. Okay? And for this we are going to use an adaptive mesh approach. Of course, we want to develop an approach which can be solved in a distributed parallel environment for computational efficiency. And then there are some issues which are intrinsic to the Navier-Stokes equations. So we will need to have a formulation which is stable, and also we will need to be able to model turbulence. Okay? So the approach that we propose and that I'm going to present today, so it's based on the use of a hierarchical adaptive mesh refinement algorithm, which is capable of focusing the computational power in some regions of the domain. We will use a fixed mesh method for the solution of the Navier-Stokes equations and for the free surface problem, which is the fixed mesh ALE method. And then we will enforce on this embedded mesh, on this fixed mesh, we are going to enforce the Turbulent boundary conditions by means of the Lagrange multiplier method. Finally, we will also stabilize the incompressible Navier-Stokes equations. We will take into account the effect of turbulence, and we are going to stabilize also the ill-conditioned cuts by using a combination of the variational multiscale method and the cost penalty method. Okay, so let me start by explaining a bit the library that we have developed in order to deal with this adaptive mesh refinement. It is called Efficiently, and it is based on a hierarchical mesh adaptation. So the basic idea is this one. We have some flow which is occurring around the cylinder, so we want our mesh to follow this flow, and for this it needs to be able to refine and unrefine the mesh. Okay? So for this we developed a library which is capable of refining and unrefining dynamically. It is capable of dealing with 2D and 3D settings, and it deals with several types of elements. So at this point we work with triangular, quadrilateral, tetrahedral, and hexahedral linear elements. It has a low memory consumption, which means that at each processor we only store the information required by that processor, and then it works by using hierarchical data structures. Okay. It results in non-conforming meshes with hanging nodes, and no balancing restriction is required, so we do not have a 2-1 balancing restriction, although we can apply it if it is necessary. Okay. We also have low rebalancing, and it is a library which is coded in object-oriented Fortran 2003, and in fact the interface is quite simple, so it is easy to couple with our finite element solver. Okay, so we also perform some scalability tests for this adaptive refinement library, and well, we have a good weak scalability up to 2,000 and even 4,000 processors, and the cost of the adaptive mesh refinement process is lower, is small when we compare it to the cost of solving a linear system in the same mesh. Okay, so this is the first ingredient that we use in our simulations, and the second one is the enforcement of Turbulent boundary conditions. This is a topic which will be discussed by Professor Ramon Codina in another talk in this mini symposium, in this workshop. But the idea, of course, is that we need to enforce the Turbulent boundary conditions in an inverse boundary. And in order to do this, we can rely on Nietzsche's method, but we developed this method, which is the symmetric link Lagrange multiplier method, whose advantage is mainly that we do not need to calibrate the penalty term, so we can develop a stabilization term which is independent of the mesh. And that's the main idea, the main advantage, and the idea is the following. So for instance, for Poisson problem, what we are going to do is to introduce a new stress field, an additional stress variable. So in this case, this is sigma, which is equal to the gradient of u, okay, for the Poisson problem. And this stress field sigma, it is on the first point is that this stress field is only defined on the elements which are cut by the interface. And the second point is that this stress field is discontinuous element to element, which means that after we write down our formulation, we can condensate this variable and end up with a problem which is written only in terms of the original variable. Okay. The main idea is to use the stress equation in order to add some terms which are enforcing the Dirichlet boundary conditions, which are these conditions here. Okay, so it works well for the Poisson problem, it works well for the incompressible Navier-Stokes equations, and for other problems, as Ramon will explain. And then the third ingredient is the adaptive fixed mesh Ailey method. So the idea is that we want to solve problems like this in which our domain will evolve in time. So as this domain is evolving in time, we need to use a formulation which is capable of dealing with this, and this is an ALE formulation, an arbitrary Lagrangian Eulerian formulation. Basically, when you introduce this kind of formulation in the incompressible Navier-Stokes equations, the main difference with respect to the original equations is that you need to take into account the deformation of the domain in your convection velocity. Okay? But at the same time, as we want to use this formulation in order to take into account the movement of the domain, we also want to use an embedded method, an unfitted mesh, in order to avoid remeshing. Okay? So we are going to deal with the movement of the domain by using an arbitrary Lagrangian Eulerian formulation, but at the same time we are going to have an unfitted mesh. So regarding the finite element approximation, so it is well known that the incompressible Navier-Stokes equations suffer from a number of instabilities if you use the standard Galerkin finite element. So we are going to have convective instabilities, then we are going to have some compatibility of the spaces if we do not want to use stabilization, a compatibility of the spaces between the space for velocity and the pressure. But also, if we are using embedded methods, we are going to have ill-conditioned cuts of the free surface over the fixed mesh. And since we are going to be dealing with high Reynolds numbers, we are going to need a turbulence model. Okay? So our approach is to add to our Galerkin finite element approximation. We are going to add two ingredients which allow us to solve these problems. Okay? And these ingredients, in the first place, are the variational multiscale method, which will allow us to stabilize convection in subproblems and also will act as a model for turbulence. And secondly, we are going to use the Gauss penalty method, which is a method which the form in which we implement this method is very similar to the variational multiscale method, because we are using orthogonal spaces for the subscales in the variational multiscale method, and we implement the Gauss penalty method also as an orthogonal projection of the gradients in the elements which are at the interface. And then by using these two formulations, these two ingredients in our formulation, so we can deal with all of these issues which we originally had. Regarding the fixed mesh Ailey method, which is this combination of the embedded and unfitted grid with the arbitrary Lagrangian Eulerian method, so the idea is not difficult. Suppose that we have a background domain, which is this domain here, and then we have, for instance, our fluid domain, which is this part here, and this is the interface in our of our fluid. So now we want to take into account the domain movement and how this surface evolves, and for this we are going to use an ALE formulation. So, since we want to use an ALE formulation, we are going to deform this domain here into this domain here as the free surface advances, but we also want to use an embedded method, so we do not want our mesh to get distorted. So at each time step, what we are going to do is to move this interface, and then we are going to project the results back onto the undeformed background mesh. Okay? So this deformation, in fact, is not done in the complete domain. It is only done in the regions which are close to the cut, and it allows us to take into account the domain movement by using this arbitrary Lagrangian Eulerian formulation, and to use at the same time an embedded grid, a fixed mesh method, so we avoid the issue of mesh distortion. So regarding the adaptive refinement criteria, so we are using this Ruffician-Lipp adaptive refinement library, and then for the numerical examples that I will show now, we are using very simple mesh refinement criteria. So we are just telling our mesh refiner to refine in those regions of the mesh in which the mesh is occupied by the fluid, and also we will have some additional refinement in the region close to the free surface. So so that we can capture properly the geometry in these areas. So there are a set of additional ingredients. Of course, we will need a level set transport function in order to move this free surface. This level set will have a reinitialization algorithm, which I will not describe here. We also have an algorithm for mass loss correction in order to avoid losing any mass in the process. And of course, since we are doing this arbitrary Lagrangian Eulerian step followed by a projection onto the background mesh, we need an efficient projection algorithm between meshes, which we have also implemented in parallel in our distributed memory set. Okay, so let me show you some numerical examples. First, we did some validation examples. In this case, this is a 2D example in which we have this this tank which is moving, okay, and then the free surface moves, and then we are studying the spatial and temporal convergence by comparing the results in successively finer meshes. Okay, so we see that for the spatial, this is for the spatial refinement, so we can see that this is slope 2. This is what we expect with linear elements, but since we have adaptive refinement, so we can get an improved convergence when we refine in the regions where this is required. Okay. And secondly, for the temporal discretization, so we also have a slope 2 with a second order time integration scheme, and this is important for us because it means that this arbitrary Lagrangian Eulerian approach is capable of taking into account properly the movement of the domain. So here I am testing the effect of the Gauss stabilization terms, the Gauss penalty method. This is the method that we use in order to stabilize the ill-conditioned cuts, and it is basically adding some terms which are penalizing the gradient jumps between elements in the interface. Okay? So this is a solution for the, in order to test this, we use a solution which is basically testing a flat fluid at rest. And then what we would like from our method is that this fluid remains at rest. So if we do not use the Gauss penalty stabilization, this fluid starts to oscillate, and these oscillations are caused precisely by the ill-conditioned cuts. Okay? So on the contrary, if we use the Gauss penalty stabilization method, so we still have some movement here, but this movement is much smaller, and that in practice it cannot be appreciated. Well, here I did not explain our mass loss correction scheme. It is a global scheme which basically it is moving the level set function upwards or downwards in order to compensate for the mass loss. So in this case we are testing a very coarse mesh with a very coarse time step. So if we do not use our mass correction scheme, so we end up with very few mass because both the mesh and the time step are very large. But if we use our mass correction scheme, the mass is conserved, and then we get some additional oscillations, but these oscillations are reasonable for this, or at least from our point of view, this is reasonable. For the level set reinitialization, I did not explain the details here, but basically we are applying our linked Lagrange multiplier method in order to enforce that after the level set reinitialization, the position of the free surface is exactly the same as it was prior to the level set reinitialization, and again we obtain nice results for this bench, for this two-dimensional test. And then this is a 3D example. This is a simple example in which we have sloshing inside a tank, inside a water tank. So in this case, again, we are using the same refinement criteria. So we keep these elements here coarse, and then we refine in the regions which are close to the free surface. What is nice here, what I'm plotting here, are the velocity vectors of the free surface, and we can see that there are no large velocities due to the ill-conditioned cuts. So we are capable of stabilizing these ill-conditioned cuts in this free surface. And then, well, maybe you cannot see it here, but this is a comparison of the experimental and the numerical results. And we can we see that we obtain a good match for these three first periods. Then at this point here, there are some differences, but this is maybe due to these initial conditions which are not exactly the same for the numerical simulation or for the experimental setup. This is another example. This is the free overflow experiment. So basically this is some fluid which is falling over this wall here. And then what is good here is that our adaptive mesh is following this fluid as it falls, so we do not invert any computational effort in the regions here. Okay, so again, the shape of this of the free surface is very similar to the experimental one. And finally, this is the dam break experiment or remote flow experiment. And in this case, so we are using the same approach. Okay, so this is there is some wall here which is going to open, and then the flow is going to start. The water is going to start moving, and it will impact this object here. So again, we are using our strategy in order to save the computational effort at this point here, and then concentrating it in the region where it is required. Again, the velocity fields are smooth, so we do not see any large or strange velocities at the interface. And finally, we obtain a good comparison against experiments, although there is a bit of delay at this point here, okay, in the second wave when it returns. Okay, so as an overview, so we have developed an efficient algorithm for adaptive mesh refinement in distributed memory parallel systems. It is based on an adaptive mesh refinement library, which is hierarchical with hanging nodes. It is nodally based. This is important because our distributed memory code is the partitions are defined on the nodes, and so this is important for us. It allows us to do load rebalancing, and we have good scalability up to 4,000 processors. And also we have shown an adaptive strategy for the simulation of free surface flows, in which the main ingredients are the linked Lagrange multiplier method for the imposition of Dirichlet boundary conditions, the arbitrary Lagrange Eulerian plus fixed mesh, so that is the fixed mesh ALU method, the stabilization of convection, INFSUP and incandescent mesh cuts through the variational multiscale method and the Gauss penalty method, and finally our adaptive refinement criteria. And then I have shown some examples which provide good results for several benchmarks.